Hello, welcome to this presentation for ECE 572. The title of this presentation is Clock Resynthesis and Crosstalk Delay Minimization. This presentation is divided into 5 sections. The first section is on clock tree synthesis. Then we would discuss capacitive coupling and crosstalk. We would follow it up with a discussion on impact of set crosstalk on clock tree synthesis. Then we would discuss minimizing crosstalk violations on clock trees. And then we would end it up with a conclusion. So let's start with a discussion on clock tree synthesis. A clock network delivers clock pulse from a source to the clock input for all sequential elements in a design. Synthesis is done post placement and pre routing in an IC design flow. Some critical design considerations are data signal arrival that decides whether there is any setup or hold time violations, clock signal arrival that decides whether there is a skew, where a skew is when clock signal arrives unevenly. In these cases, we'd have skew variations. Temporal clock period variations, which causes jitter, which is obviously undesirable. And power dissipation, since a clock network consumes a significant amount of power. A clock network synthesis problem can be defined as distribution of clock signal to all sequential storages to satisfy setup and hold constraints. In a practical design, a designer would set up a tolerable budget for skew and would be trying to optimize certain design objectives given setup hold constraints are satisfied and skew budget is met. A clock network can be synthesized under different architectures using different topologies. In a clock tree, as the name suggests, follows a tree topology with a clock source as root, clock inputs, it has a clock source as roots and clock inputs and resistor elements, also known as sinks as leaves and buffers as nodes of the trees. This topology uses less interconnects, which saves power. However, these interconnects are unevenly routed, causing skew variations. Clock trees can be symmetrical like H trees or X trees, and they could also be asymmetrical. The next topology in discussion is a clock mesh, which has a top level buffer tree connected to a grid of vertical and horizontal interconnects. Since the grid of interconnects uses extensive metal resources, power consumption for clock mesh is significant. However, this redundancy of interconnects also decreases skew variations. We could also have multiple topologies stacked on top of each other on the same network. Example, in this diagram, we have a clock mesh in a top level with a clock tree for a localized clock network. This is called a hierarchical clock distribution. A clock architecture can generally be distributed in 3 sections: global, regional, and local. A global distribution can be used to route global clocks to appropriate cores. The designs are usually symmetrical here, and we can use these skew elements here to improve our skew variations. Regional clock distributions usually have a mesh topology with higher metal interconnects for better skew. And once the grid is placed, it could be further optimized by removing unnecessary edges within the grid to improve our power consumption. In a local distribution, sinks are grouped together to create a localized clock network. So it is more of a clustering problem alongside a clock generation and placement problem. Each sink or leaf node of a regional clock is a localized root node here, and the skew consideration here is localized as well. The topologies usually used are trees and could be any one of either H trees, MMMs, geometric matching, or any of the other topologies we could use as trees. So the local distribution has its own flow going on where we start from routing. Now, since CTS is done post placement and pre routing, there are no routing blockages here. And the goal of this routing would be to produce. So the goal is similar to a normal routing on an IC where we want to produce minimum wire length to connect source to sinks, such that with the addition that we want to make sure that the skew bounds are the skew requirements are met. Post routing, we also add buffers for healthy skew and delay. This phase, however, has to respect previous standard cell placements since clock resynthesis is done post placement, and in this phase, there are certain standard cells already placed on the design. Then a post CTS tuning is done, which consists of legalization of buffer placements, making sure that the new placement that we've done of buffer does not mess with previous placements done during the placement phase, and skew corrections. Next, we will jump into the capacitive coupling and crosstalk discussion section. Um, so wires have capacitance amongst themselves, amongst their neighbors and grounds, which affects its own signals. The capacitance here is called coupling capacitance, and the phenomena as a whole is called capacitive coupling or crosstalk. When one wire, named aggressor, switches, it affects the neighboring wire, which is named victim in this case, inducing delays and voltage noises. And the direction of the switch also significantly affects the induction of delay and voltage. Switching on the same side, switching on the opposite direction has more significant effect than switching on the same direction. The factors that affect crosstalk, and three significant factors that affect crosstalk are transistor sizing, coupling, the length of the coupled interconnect, and the space between the coupled interconnect, which we can see via these diagrams. In the diagram in the left, we have four wires, sorry, five wires. Uh, we have five scenarios where in each scenario, I'm sorry, we have multiple scenarios here. On the x-axis, we have coupling length. On the y-axis, we have peak noise caused by the coupling. And each of these lines represents simulations done at differing spaces between the interconnect. So we can see that whenever the space between the two interconnects are close, there are higher coupling capacitance, which results to higher peak noise. And as the length increases, the coupling length increases, the peak noise or the crosstalk or coupling capacitance increases as well. Um, on the diagram on the right, we can see, as mentioned in the diagram on the left, that as space decreases, the coupling capacitance increases, but then the driver width of the victim, um, an increase in the driver width of the victim can negate the effect of capacitive coupling, which reduces the peak noise significantly. Coupling capacitance and its effect on delay and voltage can also be modeled. Um, so there have been certain models that model the coupling capacitance, the capacitance between the wire and its neighbor, the capacitance between the wire and ground, alongside the voltage variations and the delays that it causes. However, these are empirical models and are process dependent. In the next section, we will be discussing the impact of crosstalk on clock tree synthesis. In this section, we will see what kind of effect we can expect from from crosstalk on a clock network. Previously, we had discussed that on a clock network, a clock network has interconnects flowing through all over the IC. It consumes a significant amount of power. Symmetrical clock topologies have significant number of interconnects in parallel, and there is extensive switching caused by clock pulse. And in terms of crosstalk, It contributes to the delay and which causes skew variations, and change in voltage, which causes jitter. It is dependent on interconnect length, which is a significant factor in a clock network, and it is triggered by switching, which, as we discussed earlier, is also happens extensively in the clock network. So let's talk about crosstalk at different hierarchical levels. For global clock networks, since their interconnects are significantly longer, they are more susceptible to crosstalk, but it is pretty easy to implement shielding at this level, which significantly reduces crosstalk. Regional distribution uses higher interconnect layers, and clock meshes have grids of parallel wire switching simultaneously, so there is a significant capacitance. However, during buffer insertion in this phase, the buffers need not be limited to standard cells, and they could be custom elements designed to supply decoupling capacitances. Um, for local clock distribution, since routing is distributed, we have overall less capacitance here compared to the sink. However, ununiform topologies like H trees, MMMs, or X trees could have significantly large capacitance compared to uniform topologies. In this section, we explore an experiment where an H tree is coupled to an aggressor to varying degrees, and the results are analyzed. So as we can see in the diagram, we have an H tree set up at a 180 nanometer technology. We have a two-level H tree. Uh, the overall dimensions are 2 by 2 centimeter, which is considerably larger than you would expect in a normal circuit. The capacitive load on the leaf buffers are 150 femtofarad. Level one uses level one of the clock tree. So we have two levels. Level one is the first level H, and then we have four H configurations as level two. So level one uses metal 5, and level two uses metal 4. Um, and the and the width of these metal layers are done uh, to find. So the width are selected by essentially doing a parametric sweep to find the optimal width. Um, um, okay, so in terms of the inverters, the size of the inverter uh, is higher close to the source, and as we go further along the interconnect, the size of the buffer is decreased, but then at the end during the leaf node we have an increase in size. So we have a reduced size of buffer with each level, but then increased size at the leaf of the buffer. The propagation delay are 425 picoseconds, and the transition time are 47 picoseconds. We uh, we test this on four scenarios. Scenario A has coupling at the first level of H tree with 1 centimeter long aggressor line. Scenario B has coupling at the first level of H tree with a 0.5 centimeter long aggressor line. Scenario C has coupling along the second level of H tree on the horizontal segment with a 0.5 centimeter long aggressor line, and scenario D has coupling at the second level alongside the vertical segment with a 0.5 centimeter long aggressor line. Let's look at the results of these coupling. In terms of delay, we can see that as we um, as we decrease the space between the aggressor line, the delay in each scenario increases. It is interesting to see that scenario A, B, and C, uh, the delay in scenario A, B, and C increases more or less uniformly, but then in scenario D, there is a significant rise. And this can be accredited to the fact that in scenario D, in scenario D, the coupling was done uh, the coupling was done vertically. And if we look at the vertical interconnect, it could it is also coupled with other interconnects which essentially switch on an opposite direction. So all of the coupling that we done in this case switch on the same direction, but then in this case there are other interconnects which neighboring interconnects which switch on the opposite direction, which may have affected to this increase in delay. Here we can see the same for transition time. As the spacing decreases, the transition time increases. The increase is significant for scenario D. Here we can see the same in terms of offshoot caused by aggression on transition. As the as the spacing increases, the offshoot increases as well, and the offshoot increase is significant for scenario D. Um, in this section, we will be discussing methods to minimize crosstalk violations during clock network synthesis. We will start by defining the problem. Given two wires in parallel, we could define S max as a threshold such that if the wires are farther than X max, then the crosstalk would be negligible. The coupling capacitance in this scenario would be our effective coupling. Here, the crosstalk minimization problem can be defined as given a set of clock domains with its associated clock sinks, we want to construct a clock network in such a way that effective coupling is minimized. Our clock skew is zero, or at least under the skew budget, and total wire length is minimized. This minimization can be different for symmetric and asymmetric topologies. For an asymmetric topology, we can use a two-step method where we first cluster clock sinks for optimal skew. So a Manhattan circle, which is a circle such that the sink in question is the center and the radius is the interconnect length, which maintains zero skew. The circle is laid out for each sink, and all sinks whose circles intersect each other are clustered together. In the second step, each cluster is placed using a simulated annealing um, optimization method to optimize expected vertical coupling length, which is a function of effective coupling threshold, which is our X max, and our Y boundaries. So the result of this would be a placement and routing of an asymmetric clock tree, which has minimized crosstalk violations. For symmetric topologies, wire translocation can be used. Here we incrementally shift vertical and horizontal tracks to neighboring available tracks to reduce crosstalk. Translocation is a generalized algorithm that is useful for both CTS and routing, and we can see an example of wire translocation in play over here. So here we have a coupling capacitance violation problem. In section A of the figure, we have three wire segments, A1, A2, A3, and three power rails, P1, P2, and P3. Here we have A2, A1 and A2, which is within the effective coupling threshold. Um, this configuration is converted into a segment positioning graph, and we apply a shortest path algorithm here to find an optimal solution. And the optimal solution looks something like this, where where A1 has been translocated from 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 position 2 to position 0, which creates additional space between A1 and A2, thus effectively reducing crosstalk within the circuit. Um, Translocation can reduce crosstalk, but then can also have an impact on skew, which is handled using a crosstalk aware rerouting mechanism. Here, the critical turning points of the interconnects are placed and designed, broken into grids in a way that the points are equidistant and there are no skews. A dynamic programming based optimization is used over here to get the finalized routed interconnects. So in this presentation, we discussed clock networks, we discussed crosstalk and its properties, and we discussed how crosstalk affects clock tree synthesis. We also discussed we discussed that a clock tree or a clock network has high density of interconnects and it has constant switching, which plays a factor in the significant capacitive coupling that we have in a clock network. And we discussed different crosstalk aware routing approaches to minimize that coupling capacitance. Thank you.